Hi everyone, my name is Gregory Quinn and this is a video summary of my PhD presentation or Viva. I wanted to put this video together just to show the highlights and the cool stuff for anyone out there who's interested. So yeah, I hope you enjoy it. The title of my thesis is The Pneumatic Erection of Elastic Grid Shells, Design, Simulation and Realization. My supervisors were Professors Christoph Gengnagel, Chris Williams and Kai-Uwe Bletzinger. This thesis starts with a very simple question, namely, can elastic grid shells, like this one, the famous multi-Halle Mannheim, be erected by means of pneumatic falsework, i.e. big cushions? And in this thesis I've shown that the answer is categorically yes, they can. I put forward a novel method based on 3.5 years of research. I develop a computational simulation environment, and then I show examples of two built prototypes to validate the method. I start off talking a lot about elastic grid shells, what they are, how they are made from slender profiles or rods or beams to form a compliant mechanism which is erected into shape to become a doubly curved shell structure. And in my literature review I refer to several built examples of elastic grid shells. I compare their spans, materials, stabilizing methods, and then I relate all of this back to their erection methods. There are 3 established erection methods for elastic grid shells, the first being lift up. Check out the animated icon made using Kangaroo. Lift up involves craning cables. This method has certain advantages and disadvantages. One of the obvious disadvantages is that from these concentrated point loads in the grid, you run the risk of extremely high curvatures and overstressing of the beams. The other established method is push-up, which was used for the multi-Halle Mannheim. Here you see with these jacking towers and spreading beams. Now we can't assemble like this nowadays because modern health and safety regulations forbid the assembly of a structure that is not fully restrained overhead, so we can't do that anymore. And besides, that also introduces point loads into the grid shell, and it's not particularly safe. More recently, the elastic grid shells have been erected via this so-called ease-down method, and basically that involves filling the volume with scaffolding, mounting the grid shell at a height, and lowering it into position in a very controlled and precise manner. And this has certain advantages, but also you have to fill the volume with scaffolding, and that is associated with significant time and cost. And then the novel method, the new one, is inflate, and that's what I investigate and develop and prototype in my thesis. In my literature review, I also look at the historical precedent of pneumatic formwork and falsework, particularly with concrete shells and various other examples. The next chapter proposes the novel method based on 3.5 years of research. There are different process flows, if you like, of how one could go about pneumatically erecting elastic grid shells. And in this chapter I put forward what I think to be the most sensible approach based on my findings. For example, one of the things that I think is not a good idea is using spherical cushions. A lot of people ask me, why don't you just use a ball, as if the geometric simplicity of a ball would imply simplicity elsewhere, but in fact that's not the case, because the ball has a very a much smaller contact area with the grid shell, depending on its size, of course, but you're going to need much higher pressures inside the ball, and it's very difficult to approximate irregular shapes, which is why my proposal puts forward having the cushion exactly the same shape as the target shape. And in my case, the target shape is a funicular, but more about shapes later. Chapter 5 talks about the computational methods. I compare 3 different computational methods, but in particular I talk a lot about Kangaroo, the magic solver Kangaroo by Daniel Piker, which is based on discrete finite elements with a local stiffness-based solver. I talk about that, how it works, its customizability, its extensibility, and some of the graphical assets that I programmed for it to display forces and things like that. Then this is put in the wider context of the academic dissemination with these various academic workshops, things like that. And then I talk about another cool application of this simulation environment, namely Struct AR, or augmented reality structures. Now this is a very, very, a highly suitable application of the dynamic relaxation, projection-based dynamic relaxation solver of Kangaroo, because we have systems that are exhibiting large deflections. They may not necessarily be statically determinate. They could be a mechanism. We've got topological changes if you're switching from demos, between demos and systems. So yeah, basically this was presented as a further example of how the simulation environment can be exploited for educational means. And so moving on. Chapter 6, I start talking about the experimental results. I provide flowcharts describing how I put together each of my simulation pipelines. The flowcharts are my attempt to provide some kind of level of academic transparency to it all. I talk a lot about shape and form, in particular the funicular, pneumatic and elastica shapes, first in 2 dimensions and then later in 3 dimensions. And these 3 shapes, the funicular, pneumatic and elastica, are absolutely integral to my thesis, to my work. How they behave and how they interact with one another is at the core of my work. And so there are various studies that plot out different insights into those 3 shapes and how they interact with one another. Then I made some very early on in the thesis, I made some did some initial simulations on the existing erection methods, lift up, push up, ease down, using sophistic, so a global stiffness based solver, and there are severe limitations with what can and can't be simulated in this kind of environment. But nonetheless, these initial results help to validate the hypothesis, I suppose, that the lift up and push up methods run the risk of overstressing of the beams. Then there's also a first physical prototype. This was a case study for a 30-meter dome-shaped grid shell, but the physical model was 1/10 scale, so the whole thing was scaled using the Buckingham Pi theorem of dimensional analysis, which basically means you can artificially increase the self-weight of the structure to represent the physical properties in the real scale. And that worked. It's a very simple geometry, but this was the first ever validation that pneumatic erection of elastic grid shells works. So I was very pleased with that, and that, I suppose, that motivated me to keep pursuing the topic and see where it leads. A few more attempts were made using sophistic, so the global stiffness approach to simulate this behavior. And what we see, but basically this simulation environment has severe limitations. Going from a fully crumpled, deflated cushion to fully inflated with sliding collisions and mechanisms, just can't be simulated in this kind of environment. But a couple of hacks and things were developed. For example, the collision between the grid and the cushion here is being modelled with spring elements, which have a custom working law, so high compression stiffness and zero tension stiffness. So despite the fact that there are limitations to this modelling environment, these results were valuable in providing some insight to this, what I called the skirting effect. There's a separation between contact areas and no contact areas. And yeah, that was a significant finding early on in the thesis, because it's the pulling the beam ends to their support points is absolutely crucial to this method. More on that later. Yeah, so then in order to simulate the erection process in its entirety, this is what pushed me more towards dynamic relaxation and the kangaroo solver. So here was the first completely custom simulation pipeline I developed. This is for a single strip of grid shell interacting with a cushion, a single beam and cushion. Now this provided some valuable results relating to tethering, i.e. In this case external tethering, i.e. the cables at the beam ends which pull the beam ends to the support points. These results basically investigate at what point is a good time to shorten the cables at the edge. If you shorten them too quickly, you run the risk of over-stressing or buckling the beams too early. So basically, you have to wait till the trigger pressure inside the cushion is reached before you start shortening the cables. More about the trigger pressure later. So moving on. Then from that, from the 2D analysis, it took quite some time to get to a fully comprehensive 3D erection analysis. A lot went wrong before it went right. It took a lot of development, but in the end, I got there. And here we have the full erection simulation. And this is, there's a lot going on here. You know, there's the fully crumpled cushion colliding with a compliant mechanism, there's topological changes, there's multi-stages of the erection, and all of this is feasible thanks to Kangaroo's dynamic relaxation solver and the environment that it provides. So here we see the blue line is the internal pressure increasing at a linear rate, and when it hits the dashed line, that dashed line is the so-called trigger pressure, and that's when movement starts to occur. The second phase is when the beam ends are pulled to their support points, and the final phase is the bag is deflated. But at the end there's a resting period to allow the system to find a static equilibrium. So the deflation occurs at a slightly higher rate. And that provided some interesting results. Here we see the maximum and average bending utilization in the grid shell. And what I find interesting here is in the relaxation period at the end, we see the maximum bending utilization increase slightly, but the average bending utilization decrease slightly. And this relates to shape. When the cushion is pushing against the grid shell, it makes the whole global shape approximate or tend towards the pneumatic form. And when the cushion is removed, the grid shell is allowed to relax into its elastica relaxed state, which more closely approximates the funicular target shape. Here we see we're plotting the deviation from the grid shell to its target, and what we see is, for maximum and average deviation, is a very direct and deliberate convergence to the target shape. So it's a very efficient erection process. And again, here at the end, when the cushion deflates, we see the grid converge even more closely to its funicular target, which again relates to the shape. This animation is pretty cool because we see it's plotting the axial forces, and we see during erection it's predominantly blue, so in tension, and in the end state it switches or flips to a compression shell, which I think is quite interesting to observe. Also look at the reaction forces, the reaction of the membrane and the grid itself, but I won't go into detail here. And here, this is more about the trigger pressure. Now, the trigger pressure relates to the shell shape, pitch, so that's what this graph explains. So then I try and relate all of this data into something that is more tangible and valuable. So one thing I do propose is that the grid shell should be stiff enough to support its self-weight after erection before stabilizing elements have been added. So in this case, the tension cables. Now what does that mean? In this video, we see the cushion is no longer supporting the grid shell, it's currently deflating. The grid shell ends have been fixed in their support points. The bracing cables are slack, so not working. And you see the grid shell is able to support its self-weight, but it's incredibly soft. Now, once you fix the cables, you can see a significant jump in global stiffness of the grid shell. And of course, it's able to sustain much larger external loading when the bracing has been added. So then I try and collate all of this into a set of, let's say, a bandwidth of viability. I put forward, what works and what doesn't, relating to materials, shapes, section sizes, that kind of thing. Chapter 7, I talk about the full-scale demonstrators, the prototypes. This was the first one, the Shelter ANCB Pavilion, built in the summer of 2017 in Berlin. It's a 14-meter span structure, 3.8 meters high, so it's pretty big. It's made from black pigmented GFRP pultruded rods with actually nylon sheathed, so they're smooth to the touch. The cover is a PVC coated polyester membrane. The steel perimeter plate is 1 centimeter thick steel, hot dip galvanized, and I hope that it offers architecturally something a bit new and different. This was designed as an event pavilion, and I'm quite pleased with the result. But crucially, it worked. The erection, pneumatic erection, worked just as planned. Correlated very closely with the simulations. The assembly time of the first prototype, assembly and erection altogether, was 5 days. Erection is only about 20 minutes, but all in all it took 5 days. The same prototype was rebuilt a year later on this patch of grass right in front of the University of Arts in Berlin, and I was able to make several design tweaks and changes to the beam end connectors and the cables, such that I was able to reduce the assembly time from 5 days down to 3 days. So that was a positive development. Then in this autumn of 2018, I built a second prototype, a completely different prototype, for the Healthy Housing for the Displaced project in collaboration with the University of Bath. And this is a disaster relief shelter. Now, the shape may look the same, but in terms of design, there's a whole host of changes here. Loads and loads of things have been changed. I guess the most obvious one is that the cushion is not removed after inflation, but instead it acts as the architectural envelope and stays in situ after erection. And thanks to the even more design improvements and changes, the full assembly and erection was reduced down to just 8 hours. So I think my personal target would be that one of these shelter systems could be erected by, let's say, 2 people in 4 hours. I think that's a realistic and achievable target. I talk about certain aspects of the design, the detailing, and these beam end connectors are absolutely crucial to the viability of the method. Being able to pull the beam ends quickly to their support points is absolutely integral to its viability, which is why I spent a long time trying to develop connectors that work, that are effective. So that was, I guess, a significant design output of my thesis. I talk a little bit about the structural analysis and then evaluation of the prototypes themselves. This is quite cool. So I did a 3D point cloud scan of the first prototype on site and compared that with the simulation results. And despite the fact that this is actually quite a large structure, incredibly slender, I was really pleased with the precision. So at the top, the apex, there's only a 22 millimeter vertical deviation from the designed target shape. So I think that was a very positive result. Other interesting practical findings were the real risk of overinflation of the bag. Here I just didn't turn the blower off quickly enough, and you can see the extreme forces that such a cushion can exert. It's ripping out the steel plates and the ground anchors from the ground. But this could easily be solved with a pressure release valve. So it's something to be aware of, but actually quite a solvable problem. Chapter 8 is the outlook, and I think this is what excites me the most: the humanitarian relief application potential of the Shelter system and of pneumatically erecting grid shells. I think has huge potential. Here we see the healthy housing for the displaced Shelter prototype next to the cleverly named but not necessarily Better Shelter from IKEA. It's called Better Shelter, and I think it's obvious to see that they speak. Architecturally, they speak completely different languages. Their form factors are wildly different. And I put forward the argument that a grid shell has all sorts of benefits over orthogonal frame structures for this type of application. Not least, the structural robustness, the aerodynamic shape, the fact that the floor can be undulating, it can tolerate relatively generous geometric deviations. Now, one of the reasons the assembly of the second prototype was so much faster than the first is because the grid shell was pre-assembled into these concertina tiles, which can be popped open on site very quickly and easily, and mounted together so basically it just really speeds up the erection. So they're plonked in place, and the beams meet tip to tip. And here we see this laser-cut steel connectors, which fix them together, spin that round, put a pin in, and it's connected. Now, one of the key differences between the first and second prototype, so here we see the first prototype, the cushion is removed. This was designed as a summer pavilion that can be reused as often as you like, so the cushion is removed, and there's a second, more highly detailed architectural skin which gets pulled over the top. It's a bit more work to do, and then you compare that with the second prototype, and the cushion stays in situ. In this case is sacrificial, and so the clamping plate at the perimeter for the erection phase creates a closed air volume for the cushion, and in the end state, that clamping plate at the perimeter provides the weather-tight architectural envelope in the end state. And you see the connections between the membrane and the grid shell. There's over 100 connection points. And these connection points provide hanging points on the inside, which can be used for partition curtains or any kind of architectural programmatic application. So let's skip forwards. The erection or the speedy erection of disaster relief shelters is only one small aspect of their design. The thermal performance is of absolute critical importance, particularly in the Azraq camp in Jordan, where you have an arid climate, very hot summer days, and you need to be able to exploit night purge cooling, which is why I experimented with these large low-level venting ducts. Another cool thing about grid shells is that once they're assembled, you have this sacrificial formwork which you can climb on and exploit for any number of additional architectural skins and or thermal insulation. So this prototype will be given thermal insulation, sheep's wool, in the next few months, and we're going to do some long-term testing on that. Yeah, the hanging points provide an opportunity for programmatic architectural divisioning, partitioning, and these renders made using the Unreal Engine. Actually, there was a VR model that was on display during my presentation. This tries to give an idea of what kind of architectural quality the shelter system could offer. Another cool thing about these partition curtains is you can partition the space, but you actually still have one thermal zone with airflow. So one of the problems with the existing T-shelters in Azraq camp is that partitioning creates these really closed hot boxes, and you get internal temperatures of plus 40 degrees. Yeah, so in conclusion, what I end up with is these 8 axioms of how I propose elastic grid shells can or should be erected via pneumatic formwork. Yeah, so I think I'll leave it at that. I just wanted this to be a slightly brief summary of the presentation. I hope you enjoyed it. Thanks very much. Okay, bye.